right, so hi everyone. I'm really glad to be here at JSConf. I'm really sort of an alien here. It's not my usual crowd. I don't code JavaScript for a living. So I might bring in a bit of a different perspective on things, especially a bit more like less about code and more about the underlying concept. So also, if you've been at Stephanie's talk, you'll see some of the same concepts explained in a bit of a different way. So hopefully it'll be interesting. This is me with some hair that I don't have anymore. And this is how you pronounce my name, Txus, if you read phonetics. So I work at Codegram, an agency in Barcelona. We put on quite a cool conference as well in Barcelona called Full Stack Fest. Check it out next year if you want. It's pretty nice. OK, so we're here to talk about abstraction. And abstraction, we have sort of a love-hate relationship with it. We love it because it's what our programs are made of, but we hate it because when there's too much of it, or we think there's too much of it, then we're just frustrated. We fail to see the sort of the essence of the problem. But I would argue that actually it's just about the level of abstraction we're comfortable with, and like everything, it can be trained, and you can learn about being comfortable with higher levels of abstraction. So we'll see a bit more about abstraction with an example. What do you see in these two pictures? In a way, they depict different things, but in other ways, they are the same thing, right? A computer would have a hard time maybe finding out that they are the same thing. But we already know. Your brain just looks at these pictures and says, oh, of course, I know what it is. It's a dog. So you've never met these two particular dogs here, these two. But you already know a lot about them. You know what they eat, more or less, or that they like to go for walks, and that they don't like cats. Maybe they do, but in general, probably they don't. So it's pretty useful. You see two dogs that you've never seen before, and you already know a lot about them, just because you identify them as a dog, this concept that you have in your mind with a lot of semantic knowledge attached to it. You're forgetting their differences just to sort of understand the essence of them. Now, I'd like to share a story that I didn't write, but I really like. This Argentinian writer, Jorge Luis Borges, you should read it. He has a story called Funes de Memorios. And in this story, basically there's Funes, who is a young man who once fell off a horse and just hit his head with a rock or something. And then from that moment, his memory became perfect. He could no longer forget anything. So every instant of everything, he would just remember forever. That means every smell, everything he saw or heard or anything. And that brought him to experience the world in a very different way. So, for example, he started undertaking this bizarre experiments. Like, for example, he started devising his own numerical system. And Borges, who is a character in this story, asked Funes, so what is this thing you're working on, this numerical system? And Funes was like, oh, well, you know, I'm assigning a name to every number. So the number 4 is dog, and the number 7 is staircase, and so on. And he just wrote them down in his notebook. And Borges was confused, and he was like, but why would you do that? Isn't that the opposite of a numerical system? You cannot reason about this. If you have like thousands and thousands and millions of numbers with different names, you cannot do arithmetic or anything useful with them. But Funes wasn't interested in that. And Borges brought up a point that John Locke, the philosopher, he envisioned once an impossible idiom, a language where every single thing has its own name. So every instance of every branch, every leaf, everything has its own name. So there was no such thing as a leaf. There was this leaf, and that, and they all had different names. Of course, Locke dismissed that as just sort of useless because he thought, well, you cannot reason about anything or communicate to another human being what you've seen if everything has its own name. So you cannot talk about things. But Funes reacted to that very differently than what Borges expected. Funes said, well, that system is way too general. Actually, every instant in time of every of these objects should deserve its own name, because it's essentially different. It changes over time, right? So to him, a dog seen from the side at 3 p.m. had a different name from the same dog seen from a different angle one minute later. They were just different things. And arguably they are. It's not a solved problem in philosophy, right? Identity. So we tend to think that we know what identity is. We look at a thing, and 2 seconds later we look at it, and it's the same thing, or we treat it as the same thing. We look at a person, we meet them 10 years later, and we know it's the same person. But is it? I don't know. It's not a solved problem. But it's sort of a useful abstraction that we have. And Funes couldn't abstract over that. So as smart as Funes seemed with his incredible memory, Borges made the point that he thought Funes wasn't really capable of thinking, because thinking is to forget differences, to generalize, to abstract, Borges argues. So we'll see that abstraction is something way deeper than just forgetting differences and just losing detail. It gives us something in return. So yeah, arguably dogs, actually losing detail with dogs is sort of a shame, because different dogs might behave differently and might have different properties that we're interested in. But in the world of programming, we have much simpler domains. And some of those have really interesting properties and abstractions that it's really interesting to discover them. So we'll start with one of the simplest things we can think of. It's addition. So we'll start by adding 2 numbers. We all know how to add 2 numbers. And we also know how to add 2 strings by concatenating them. Then, to us, it's actually the same as just concatenating 2 lists. So it's not a problem. We understand this. Oh yeah, just you can concatenate lists, strings, and numbers. In numbers, it means addition. Then we could say that these things, you can add them together and you get a thing of the same kind. It's a different thing, but it's a thing of the same kind. We also have an interesting property in addition. It's associative. That means no matter where you put the parentheses, you always get the same result. In numbers, it's true. In strings, it's also true. And in lists, it's also true. So we're starting to see a thing that is common to these 3 seemingly completely different things. Associativity. Then now it gets interesting. There's this number. It's called 0. And it's really interesting. It hasn't been around for very long. But it has an interesting property. If you add it to another number, you get the original number back. So it doesn't do anything. That might seem boring, but we have the same for strings and the same for lists. So what's interesting about this number? Well, this element, what we call the neutral element, or the sort of the 0, if you add it to another thing, you get the other thing back. By knowing that something adds associatively and has a neutral element, be it a list, a string, or a number, we can, for example, fold or reduce over a list of those things, starting by the operation, addition, then the neutral element, in this case 0, and a list of numbers. We can do the same with strings, folding over a list of strings, starting from the empty string. We can do the same with lists. This is sort of pseudocode, but it would be reduced in JavaScript and, yeah, a plus operation. So we see that if these things have these properties that we just described, you can fold over a list of them. The important thing is that we only assume these 2 properties of those things. So we don't know that they are numbers or lists or strings. It doesn't matter. Well, that's too easy. Yeah. Lists. So I had to put an animated GIF because I didn't have any in my presentation and everyone else had, so I had to. So I put this one. I hope I chose well. So this is too easy. Numbers, strings, lists, this all just sounds very primitive. Probably it's a coincidence that they behave the same way. But I don't think so. I'll show you something a bit different, really radically different than numbers, strings, and lists that behaves the same way. What happens when we compose two functions? We can understand that as adding two functions together, because we get a function at the end that is somehow the addition of both. So if we compose two functions with a plus, just let's imagine that that's the composition operator, you get the same as applying g to x and then f to the result of that. Now, functions add associatively as well, or compose associatively. So yeah, that works out the same way. And interestingly, now we need a neutral element for functions. That seems a bit more different. What's the zero for functions? A function that does nothing. Well, that would be the identity function that just returns its argument. That really does nothing. So if you compose f with the identity function, you get f back. It's the same. So it seems that the same things hold for functions as well. So theoretically, we could fold over a list of functions, starting with the identity function. And it works. The point here is that it's not only about functions, or lists, or strings. It's just about these two properties that we know of them. So there are many other things that in your code bases you can see and you can identify as things that add associatively and have a neutral element. You just need to get a little creative, just squint your eyes a little bit and see, I think this behaves just like that, even though it's completely different. So these two properties, associative addition and neutral element, sort of a mouthful to say all the time. So someone gave them a name, and it's a scary name, but it's not scary once you understand what they are. So there's just like these two things. People call them monoids. So that's all they are. Things that have these two properties. Now let's talk about things in plural, because I'm saying things all the time, just to clarify. We have arrays, lists, and sets in our day-to-day, or maybe just arrays like most of the time. But let's abstract over that and just talk about collections of things, a collection of T, a collection of integers or strings or whatever. Now, a collection is a thing that represents 0 or more things. And what we can do with them is map over them with a function, right? So that is a way to transform the elements in a collection. The interesting thing is that if the collection is empty, nothing happens. You get an empty collection back. That might seem normal and just boring even, but it's interesting. We'll see why in a minute. So as you expect, if you map increment over a list of integers, you get a list of integers back incremented. Empty list, you get an empty list. So that's easy enough. Then we have a different kind of collections that represent 0 or 1 element. And those we call optionals, or options, or maybes, depends on the language. Now, we can also map over those, because they are sort of the same sort of container. So we can transform the element if it's there, and don't do anything if it's not there. It's like an empty list, right? So we can map increment over sum 1 and get sum 2, or just over none, you get none back. So it's sort of like a list of one element. But then there's something a bit different that behaves exactly the same, and it's futures. Futures are just things that represent an eventual value, so eventually x or an error. So it's something in the future that will either return a value or yield an error. But we can also map over those, because if we think of them as just these sort of containers, we can transform the value whenever it exists and just don't do anything if there's an error or do something else. Now, this cannot be a coincidence. These three things that are wildly different, especially the future from the rest of the things, they behave the same with the function map. So there must be a function map that captures the essence of this operation, mapping over a thing. To understand that, we'll start calling these sort of different things like futures, collections, and optionals. We'll start calling them boxes or pots, like in Stephanie's talk. So let's talk about boxes. Doesn't matter what it is, just a box. So just knowing that a box be it a future, optional, or collection. If we map over it with a function, it applies the f function to whatever is inside the box in the way the box sees fit. So each box has its own semantics. Returns the result in the same kind of box. Now, I cannot stress enough. It applies the function in the way it sees fit. We do not get to say, no, apply this function 2 times to the first element or 3 times to the element that will be eventually or whatever. The box knows what to do. It applies the function however many times it wants and exactly when it wants, if at all. So it has a lot of power. It's not just a dumb container of things. This might remind you of encapsulation. If you've done OO, this is sort of a holy cow of OO. And it is for a good reason. And these boxes have also sort of the same properties. You shouldn't reach into them and try to get the values out of them. If you have an empty list and you try to get the first element, what do you get? Nil, null, undefined, an error, your computer freezes. You don't want to go there. The same with optionals. If you have a none, a thing that has nothing in it, if you try to extract the value, what do you get? And if you try to await for a future, basically means blocking the thread until the future realizes its value, which is not ideal. You should never block the thread. I shouldn't even have to say this here. So let the box decide. That's the whole point of boxes. So it doesn't matter what the box is, it will do the right thing. And that's a powerful thing because the only thing we need to learn is just the function map. And with that, we can do all sorts of things with futures, optionals, and lists, and many more things. Now, this has a name. These boxes are called functors in sort of, I don't know, academic speak. So if you ever see this word, this is just boxes, nothing else. Boxes that you can map over with a function. So no problem there. Now, this is quite a lot of power, the map function. But it's not the only function that we can use. There's other things. Especially, there's the case where a function yields another box. So you end up with nested and nested and nested boxes. If you have a box of t and a function from t to box of u, if you have more of those functions, you end up just with nested boxes. And that's just not, you cannot just map over that with that. I mean, that's not always a problem, but it usually is. So more concretely, if we have a collection of strings and a function from string to collection of strings, let's say we have this string and we want to split it by comma, and then split by dot each of those elements, we end up with a nested list. The problem with a nested list is that if you want to keep processing it, you need to know at which depth you're operating. Where are the strings? Just like at the first depth or second or whatever. This is not a good thing because this basically doesn't compose. If you pass this to another piece of code, the code now knows which depth it needs to operate at, which is not good. So if we want to do this, there's this handy function, flatmap, that basically is like map, but it concatenates the results at the end. It flattens the collection, right? So we get, instead of map, we use flatmap, and we get on with our lives. It's just everything is flattened, and you can keep processing each element. If you have optionals, an option address and a function from address to option street number, because everything in addresses is uncertain, you end up with a nested sum, or like a nested option. And that's not good, because you might even end up with a nested, or with just a none, which is like not nested, or a sum, something, which is nested. So you don't even know deterministically what's going to happen. Like, what depth are you going to have to operate on? So that's a no-go. If you do the same with optionals, because we've seen that they behave like lists, basically, you can also flat map over them and concatenate the optionals, which means just flatten them into a whole thing, which would be a none if either is none, or a sum if it's actually a sum. And finally, the same thing can be done for futures. If we had a code that calls an API, and gets a future of repository from GitHub, and then a function that takes a repository and knows how to fetch its followers from the API as well. This is the same case. Like, if you keep just going back and forth to the API, you end up with nested futures, and it's a mess. What you want is flatmap, and it's exactly the same. We see that it flattens the feature just as if it was a list. Now, flatmap for boxes means that it applies f to whatever's inside the box in the way the box sees fit, just like map, and then flattens the result, presumably a nested box, into a single flat box of the same kind. With its own semantics, futures, just wait until one feature returns and then do the next thing, or optionals basically give you a sum if everything went well, and a none if something went wrong. So that's, each box has its own semantics. So whenever you find yourself with a thing, a box, and then function from T to box of U, a function from U to box of V, and so on, these sort of deep functions, what you want is monads. It's exactly what the flatmap function. That's all it is. It's also called bind in some other languages, but it's called flatmap in Scala and other there's so many names for the same thing, but whatever. Flatmap is good, because it makes you think of map and then flatten. So now, as a recap, we saw that just by knowing these two things, associative addition and neutral element of anything, we can fold over a list of those anythings. We don't need to know anything else about it. Then we know that if we have a box, doesn't matter what kind of box it is, and I assure you there's hundreds and hundreds of different kinds of boxes, you can use map with your function, and it will work the way you intuitively expect. And with flatmap, it works when you have functions that create nested boxes and you want a normal box back. So now that you've seen all these abstractions, you only need to go to your own code bases. Like, just make like this a little bit and see in your own code, oh, this looks like a box that you map over. Or this looks like a thing that produces a nested something. And even though you didn't have names, maybe some of you did, but many of you didn't have names for that before. Now you know what they're called, and you will recognize them in your own code. And then you will know there's map and flatmap to your rescue, basically. So I dare you to go to your code bases and look for these patterns. And also the monoids we were talking about. For example, you could think of validation errors as things that add associatively and have a neutral element, which would be the lack of errors. And then you could just fold over a list of validation errors and have just a bigger validation error or just success. So things like that. Just be creative with like identifying and spotting these things in your own code. Finally, I'd like to thank Jessica Kerr for encouraging me to do this talk and like guiding me through the sort of the topics. And I don't think we have time for questions, do we?